Condenser bushing field grading. The bushing is used to pass the conductor into the oil filled tank of the transformer. Typically, there are two areas where electric field stress is high: at the conductor surface and near the tank wall. We use the bushing condenser to redistribute electric potential more uniformly and reduce electric field stress in the insulation. The condenser grading is designed to maintain the same capacitance between foil layers. It is achieved by varying the foil layer's length and the spacing between the foil layers. The last foil layer is grounded. The layer before the last is used to connect the diagnostic tap. Our task is to calculate electric field stress distribution at the rated voltage and to measure the capacitances between the flange and the diagnostic tap and between the diagnostic tap and the main conductor. Rated voltage is 72.9 kV AC. Bushing features rotational symmetry, so I'm going to build a two-dimensional axisymmetric model. Okay, let's start QuickField now. In QuickField, I create new problem. Bushing. Next. Problem type is AC conduction because the bushing operates at AC voltage. Bushing features rotational symmetry, so the model class is axisymmetric. Length you need some millimeters. Frequency 50 Hz. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. I already have the drawing prepared in the CAD system, so I will import it. Here is the model. You can recognize here the conductor, the insulator, inside is the oil, and this is the condenser. In axisymmetric problems, the axis of rotation is a horizontal one, so let's select everything. Move selection, rotation by 90 degrees. Then switch to insert mode and draw the horizontal axis, the axis of rotation. Then switch to select objects mode, select and remove all objects located below the axis. Okay. In fact, the electric field is distributed not only in the oil and insulator, but also in the air outside and in the oil. QuickField cannot calculate electric field distribution in the infinitely large space, so I need to limit the simulation domain. Switch to insert mode and draw the simulation domain boundaries. And I will draw the edge here. This region would be oil. Now let's assign labels. Through labels you can explain the geometric object's meaning and provide the physical properties. Switch to select objects mode, click the object to select and type in the label name here. This block is air, this block is oil, and this block is oil too. Let's zoom in, switch to select mode. This is insulator. And here we have layers of the foil and the layers of the paper insulation. Let's zoom out and use the rubber band to select. These blocks are paper. Now let's zoom in This block is not paper, this is insulator. And this block is a conductor. I didn't assign labels to the conductor borders because there is no electric field inside conductors. Instead, I'm going to assign label to the conductor faces. Let's select faces, and this one, and this one, and this one. Hold the Ctrl button pressed to select multiple objects at the same time. Now you see the edges, the vertices, and the blocks are selected. I need to assign labels only to the edges. Find the edges in the list. This is the flange, which is usually grounded. Okay, zoom to fit, and I need to assign label to the high voltage conductor. These edges belong to the high voltage conductor. Okay, let's zoom in. And I need to select these edges as well. Zoom to fit. Okay, all the edges belonging to the high voltage conductor are selected. And I assign label to the edges high voltage. Condenser consists of the layer of the foil. And for each foil layer, I should assign label. Layer 1, layer 2, layer 3, 4. Okay, I have assigned labels to the oil foil layers, and we have here the specific layer which is called the tap layer. It's rather thick, so you see it has two edges. I assign label tap. And the last layer is grounded. 0. Now let's provide physical properties for these labels. Double-click the label name in the tree. Electric permittivity of air is 1. Electric permittivity of insulator is 5.8. For the oil, 2.2. And for the paper insulation, it is 3.6. The last term in condenser, 0, is grounded. I assign 0 electric potential, and all intermediate terms are just floating conductors. Flange is grounded, so electric potential is 0. Tap is usually grounded, so again electric potential is 0. And the high voltage part, electric potential is 72.9 kilovolts. And remember, this is the root mean square value of the AC voltage. In QuickField here, I should specify the peak value, which is times square root of 2 more. Okay. Now the geometry model and material data are ready. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. The problem has been solved. Let's take a look at the results. Here you can see the electric potential distribution. And I'm interested in the electric field stress distribution. So change the presentation type. And I believe the most stressed part should be here, near the flange. Let's zoom in. If you hold the mouse over the picture, you will see the electric field stress value in the status bar below. And I'm going to use the contour tool to get the electric field stress distribution along the contour in this cross section. Just draw the contour line here and open the XY plot. This is the electric field strain distribution. The exact values you can see in the table, and here you can change the tabulating step to get more detailed results. Radius, electric potential, electric field strain. Okay, my first task was to get electric field strain distribution, and my second task is to calculate the capacitance. The capacitance is the ratio of electric charge to the potential difference. Often it is more convenient to use another equation. The capacitance is the doubled value of the stored electric field energy to the potential difference squared. To properly use this method, we should apply the potential difference only to one pair of electrodes. Other electrodes should be disconnected so that electric field is produced only by a single pair of electrodes. Okay, imagine that the bushing is in the laboratory. To measure the capacitance between the conductor and the tap electrode, we would apply some voltage to the conductor, say 500 volts, and the tap would be grounded and the flange would be disconnected. Floating conductor. Now let's again solve the problem. Let's take a look at the results. Remember, we are in the laboratory. Test potential difference is applied between the tap electrode and the high voltage conductor. Now let's calculate the stored electric field energy. Again, I'm going to use the contour tool. Click the edge to select the boundary. The contour should be counterclockwise directed. Contour close. Integrals. I need to find the stored electric field energy. Here is the value. Let's put it here. The energy. The potential difference is 500 volts and the capacitance is energy value doubled divided by the potential difference squared. This is 218 picofards. Okay, now let's measure the capacitance between the tap and the flange. I should disconnect the high voltage conductor from the voltage source. I will apply the voltage to the tap and the flange will be grounded. Let's solve the problem again. Let's take a look at the results. Remember, we are in a laboratory. The potential difference is applied between the tap and the flange. Let's zoom in. This is the tap, double line, and this foil layer is connected to the flange. Again, I'm going to use the contour tool to select everything and calculate the stored electric field energy. Contour close, integrals, energy. Copy this value and paste it here. Now the capacitance in picofards is 7173. This is the capacitance between the tap and the flange. So this way we were able to calculate electric field stress distribution in the bushing and measure the capacitances. If you search for the condenser bushing on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.